All right, hello, lovely humans. Welcome to part 2 of Fourier series. Yeah! In part 1, we focused on the y of Fourier series, and although I focused pretty much exclusively on how Fourier series are used to convert sound waves into digital signals using a Fourier series, anything that repeats over time can be broken down into a Fourier series. So things like vibrations, so resonance is a good example of that, or oscillations, so like a pendulum swinging back and forth, or an object on a spring moving back and forth, or up and down, or whatever, or your slinky going down the stairs, can all be represented with Fourier series. And a quick note to mention that although Fourier series can only be applied to functions that are periodic or things that repeat over time, they come back to the same value over a certain amount of time or a certain amount of space, we can use a different but kind of related technique called Fourier transforms to represent functions that are not periodic. So that was at the heart of the question that caused me to do this series. So I will get to Fourier transforms, but we have to understand how to do a Fourier series first. Okay, so I left you with the generic formula for a Fourier series, and so I'm going to rewrite that up at the top so we have it for reference. Okay, so a given function can be expanded in a Fourier series by using the general form, which looks like this. Cosine of x plus a2 cosine of 2x plus dot 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 plus b1 sine of x plus b2 sine of 2x plus dot dot dot. And then I left you by saying, okay, so given a particular function, we can expand it in a Fourier series by finding these specific coefficients. And then I was like, good luck, okay, bye. That's what part 2 is for. Okay, so in power series, we are able to apply boundary conditions basically by putting constraints on a given system. But if we, boundary conditions kind of imply a start and an end. So typically we'll understand where something is starting. Like, for example, if I am holding a ball and I drop it, I know that the ball starts at a certain height and that it is not moving. And when I drop it, I know that eventually it's going to hit the ground. And so I can kind of constrain my problem by placing it in a box, so to speak. But sine and cosine continue on forever. So how do we place them in a nice little box? Well, we can't, because we don't really know where they start or finish. But fortunately, we don't have to come up with the boundary conditions, quote unquote, on our own, because mathematicians have been doing this for hundreds of years, and they realized that instead of starting and ending conditions, we can use average values. Yeah! So because our functions repeat over time or repeat over a given period, we know what the average values should be. So to look at a specific example, sine starts at 0, goes down and up like that, and then comes back. So this is a period of 2 pi, and this is 0. And so in this case, if we were to ask what is the average value of our sine function, this is going to be sine of x, over the interval from 0 to 2 pi, we would say, well, wait a second, these two chunks are equal and opposite, so the average value is actually 0. Ha! Yep, exactly. So we're just going to use this basic understanding to apply some constraints that allow us to find these coefficients. Okay, but what does that general formula for average value look like? So the average value is going to be equal to the integral over some interval of our function f of x with respect to dx divided by the distance of that interval. And so just to give you an example of what this actually means and how it's actually connected to calculating the average for something, where you just add up chunks and then you divide by the total number of chunks. It's the exact same thing, but instead of discrete or specific objects, we have infinitesimal slices. So we use an integral to find the area. Let's say this is A, this is B. We add it up, and then we divide by the length or the size of that interval. So it's really the same exact equation for finding an average, but it uses an integral instead of a summation sign. Pretty cool, right? Yeah, I think so. Okay, so this is going to be the equation that we then apply to find our coefficients. So, to find, well, I'm going to give you a little bit of a hint. We're going to find A0 first and then use that to find generic formulas for AN and BN, which are basically, would allow us to find the coefficients for cosine as well as sine. Okay, so like in my textbook, we are going to use a period of 2 pi, and so we're going to go from the interval negative pi to pi, and then we are going to apply this equation to this formula. So that looks like this. The interval, well, first let's calculate what b minus a is. So b, I'll just say a comma b. So a is going to be negative pi, and b is pi. So pi minus negative pi equals 2 pi. Boop. So then this equation becomes 1 over 2 pi. Since it's a constant, we can take it outside of the integral. And we're going to have negative pi to pi f of x dx. So that is the left side of the equation, and now we apply it to each term in the right side of the equation. So this first piece is pretty straightforward because it does not depend on x. So we just have 1 over 2 a naught times 1 over 2 pi times the integral from negative pi to pi of dx. You can kind of think of like a 1 being there. So that is this first term right here. Whoop. I have colors. Ooh, I'm going to use colors. Okay, so this is this. Boop. Okay, and so now we just add and go term by term. So we have, I'm going to go far over because this is going to be a little long. Okay, so now we have a1 over 2 pi times the integral of negative pi to pi cosine of x dx plus a2 over 2 pi negative pi to pi cosine of 2x dx plus b1, oops, plus dot dot dot, plus b1 over 2 pi negative pi to pi of sine of x dx plus b2 over 2 pi, same interval, sine 2x dx plus dot dot dot. Okay, so you can see how this gets a little tedious. I'm going to grab my other colors so we can show where the cosine terms are, just pull it out a little more obviously. So these are our cosine terms that would keep going, and grab my color. And these are our sine terms. And again, they would keep going. Okay, so now we take this and we start to see what pieces we can get rid of. So since we have been working with this for a little bit, I'm going to erase this. And we are going to look at this part first. So let's simplify. a1 over 2 pi, negative pi to pi, cosine of x dx. Okay, let's actually solve this. So the integral of cosine is sine, or 2 pi, and we don't need to worry about constants because we have an interval. So sine of x from negative pi to pi. And then we just solve for that. So we get a1 over 2 pi, sine of, we're going to get sine of pi minus sine of negative pi, but sine of pi is 0. So we are going to get 0 minus 0. Oh, look at that. This term goes to 0. Check. Okay, and just to show, let's do the second term for cosine. I encourage you to do this and follow along with me to get practice with how we do these types of integrals. It's really not that bad once you get the hang of it. Okay, so this second term is going to be negative pi to pi cosine of 2x dx, and that's going to be 2 over 2 pi. This factor of 2 is going to come out, and we're going to get, again, sine of 2x from negative pi to pi. And then this one simplifies. We're going to get a 2 over 4 pi sine of 0 minus sine of 0. Oops, sorry. I got ahead of myself here. Sine of 2 pi, negative 2 pi, but that goes to 0. Okay, so look at that. This second term also cancels. Ha-ha! We are simplifying super quick. Okay, and then the last one that I'll do is B1, because again, it extends in the same way. The higher order coefficients basically are the same thing that happens with the cosine. So let's see what this equals. B1 over 2 pi from negative pi to pi of sine of x dx equals B1 over 2 pi negative cosine of x from negative pi to pi. That's going to be B1 over 2 pi cosine of pi minus cosine of negative pi. This goes to negative 1, and this also goes to negative 1. Negative 1 minus a negative 1 equals 0. Look at that. That's very convenient. Okay, so this goes to 0, and in the same exact way, this goes to 0. Cool. So now, all of a sudden, all that we are left with is just this first term. So that will allow us to solve for a0. So let's solve this integral and then simplify our equation. So 1 over 2 a naught, actually let's write that a little bit more compactly. So we are going to get a naught over 4 pi, integral of negative pi to pi of 1 times dx equals a naught over 4 pi times x from negative pi to pi, and that's just going to be a naught times pi minus a negative pi is pi plus pi, so that'll be 2 pi over 4 pi. Oh, look at that, that cancels, and that becomes a 2. So a naught over 2. Okay, so this is all that is left of the right side of this equation, which actually had infinite terms. Ha ha! Super cool, right? So now all of a sudden we have a manageable equation to find the first term of our series. So I'm going to erase this, and we are going to solve for a naught. So this ends up being a naught over 2. Okay. So then if I multiply both sides by 2, I get 1 over pi f of x, oops, need that little interval there, f of x dx equals a naught. Ha! I guess we could also write a naught over here, as it usually is more appropriately in mathematics. Okay, so now you're like, well, wait, how do we actually find a naught? What is f of x? Good question. So this function is what you would be given, it's the function that you are expanding with the Fourier series. So in my math textbook, we are given this function to start with. If you are given a real world example, you basically will be able to find a representation for f of x that you then plug into this equation. So then the next question would be, well, if we already know f of x, why are we expanding it in a Fourier series? There are a lot of reasons. One is if we have what is called a discontinuous function. So let's say, for example, we have something that looks like this. We can represent this pretty easily on paper, but not necessarily very easily in a circuit or on a computer or in a different type of situation. Or even if we want to take the integral of a discontinuous function, we can't really, or I guess we can, there are some different tricks, but by using a Fourier series, we are able to convert a discontinuous function, something that has a lot of breaks in it, into something that is continuous, and then we can manipulate it a lot easier. So there are lots of different reasons. But you will be given this function, hopefully. Or you'll have to suss it out from the real world. But you will be able to figure out what this is, and then using this this equation, you can find a naught. Okay, so we have an equation for a naught, but what about the rest of the coefficients? What? Okay, so really quickly, basically what you do is you multiply the average value function, both sides of it, by cosine of nx. So what that ends up looking like, I'm going to give you the result because I don't want to talk forever. So when you do that, you're going to get this. X times cosine of nx dx. And for bn, you just multiply both sides by sine of nx. Boom, there you go. And that is how you find the coefficients for any given function that you are trying to expand in a Fourier series. So again, you will be given the function, and then to find each of these coefficients, all you do, it's not super easy, but it's also totally manageable once you understand how to run these integrals. So you just, you can find each individual coefficient by replacing n with that number, or you can do it generally and keeping in mind what n means. N is just an integer. It can be a positive or a negative integer, so you have to keep all of the possibilities in your head at once. But cosine and sine, since they're periodic functions, we can use that to our advantage, which we will see when we do an example. Okay, so I'm going to leave it there for now. These are the formulas to find the coefficients, an for the cosine terms in your Fourier series, and bn for the sine terms in your series. Please let me know if you have any questions about how we applied the average value function. We are also I'm assuming a certain level of knowledge about taking integrals, dealing with sine and cosine, so let me know if you have any questions about that, or anything else we talked about here. All right, cool. And now check out part 3 for a specific example of Fourier series, which I think will make it a lot more clear as to what Fourier series are really useful for, as well as how we actually apply these equations. All right, so we'll see you there. Yay, bye!